All right. Good morning, all. Good afternoon, folks. Hello, wherever you are. I'm James Posielski. I'm the, I guess now, former chair of the Systematic Review and Meta-Analysis SIG. And this is our online seminar series, the last one for spring semester of 2025. Today, we're honored to be joined by Dr. Richard Wiley, who's a professor of biostatistics at the University of Birmingham. Dr. Riley is really a world-leading expert in all things synthesis. He's worked on topics ranging from multivariate meta-analysis to individual participant data meta-analysis, as we're going to be talking about today, and predictive modeling in healthcare. I've been following his work since I was a young pup of a graduate student. I feel like I've been chasing his heels for years, really, and found many of his pieces to be really important for figuring out what's going on in the world of meta-analysis. So his topic today is individual participant data meta-analysis. It's an area where there's many applications in the world of healthcare, but it's still kind of an emerging thing in education and some parts of the social sciences. So I'm very excited to have him here today, and it will follow our usual rules. I think he'll be presenting for about 45 or 50 minutes. If you have questions during that time, you're welcome to leave them in the chat, and we will kind of collate them. If it's okay, I'll interrupt if there's any really burning questions. Otherwise, we'll use the chat to seed our discussion at the end. With that, please join me in welcoming Dr. Richard Riley.
Thank you so much. It is a real privilege to be speaking with you today. Um, I think one of the most important things we can do is share our knowledge and to be able to do that with you guys. And I think, I was just saying this before, in the world leading seminar series on systematic reviews, is a real privilege for me. So hopefully you can see my screen and it's the right screen. Just take that off there. And yes, so individual participant data meta-analysis. So today I'm going to be, I'll just get rid of that. I'm going to be talking broadly about the IPD meta-analysis field. So this is not going to get statistical. This is a talk that's intended for everybody. So really what I want to be doing is showcasing the rationale for IPD meta-analysis and the key steps, talk broadly about statistical methodology that we can use and pros and cons of different types. I also want to litter this with notable examples about why IPD meta-analysis is useful, not just spanning trials, but also going into other areas like prediction modeling. And then I want to finish with some notes of caution because it's not all perfect in this field. Okay, so let's crack on. So part one, rationale and key steps. So you're all going to be familiar with what meta-analysis is. But obviously it's a statistical analysis that comes towards the end of a systematic review where you're pulling the results together to come up with some overall summary findings. From the Greek, after, above, or transcending, I love to think that I'm the analyst that transcends everything that's gone before. So as meta-analysts, we transcend everything that's gone before. Whether that's true or not, I doubt, but that's the way I like to think about it. So traditional meta-analysis, as you will all know, uses what I refer to as aggregate data. So these are results or summary information from publications. So if you're looking at meta-analysis of RCTs, we'd be looking at extracting measures of treatment effect, like the odds ratio or the risk ratio, and a measure of uncertainty around that estimate, like the standard error of the estimate or the confidence interval. So advantages of this approach, is quite familiar to most people. In theory, at least, it's quick. If studies are well reported, you extract the information. We can use well-established meta-analysis methods that are embedded in software. We could even use Excel to do some very basic meta-analysis, such as the inverse variance method, Mansell-Hansel method, and other methods that we know and perhaps love or hate, like fixed effect or random effects meta-analysis. Um, like I said, we got suitable software available. We get nice forest plots, nice visual summaries. Here's an example, a meta-analysis of 10 um, antihypertensive trials. So looking to see if antihypertensive treatment reduces blood pressure. I've got 10 trials in this meta-analysis. I've pulled the results and I get that the average pooled effect is about a 10 millimeters of mercury reduction in blood pressure compared to control. And there's some heterogeneity across studies, but all the studies are suggesting that the treatment is beneficial, um, as we might expect. And this is an example I'll come back onto as we go on. Um, but what are some disadvantages of that? So, if we're going to studies to extract information, then we're going to be reliant on the reporting quality of those published articles. Now, still, even in this day and age, we're faced with reporting problems. So, we don't get all the results that we want. Sometimes, particularly for the non-significant results, we might just get p-values rather than effect estimates. As a statistician, I like to be in control, but if you've not done that primary study yourself, then you've not chosen the analysis method. So there may be inconsistency across studies in the choice of effect measures. Some may give hazard ratios, some may give odds ratios. Some may adjust for prognostic factors, some may not. Some may ignore clustering, for example, by center in a trial. Some may examine non-proportional hazards, some others don't, etc., etc. If you're not in control, you have no control over how the analysis was done or what was reported. This all leads to potential threats of publication bias, more significant the result, the more likely you are to see it. And outcome reporting bias. So even if all studies are reported, there'll be some outcomes that are not reported or are hidden simply because they weren't deemed to be important. So some limitations. It's very hard to go beyond the original analysis. So if you want to examine proportional hazards or develop a prediction model, you can't really do that because all you've got is the summary information. So you've lost the participant, the individual level information. So if you think of a statistician, statisticians typically want to explain and understand variability. Now, in meta-analysis, the variability that you observe in a typical meta-analysis is the variability across studies. So that's how, let's say, the treatment effect estimates vary across studies. But if you think about healthcare and treating individuals, what you're really interested in a lot of the time is variability across individuals. But without with only summary data, you don't really have any information about what the variability is across individuals. You can just understand variability across studies. So I can't look at individual level prognostic factors. It's hard to look at subgroups defined by individuals. It's hard to look at interactions between treatment and patient level covariates. So what I'm saying is it's very hard to see whether some individuals do better than others. We can look at average and how population levels are doing, but we struggle to go beyond that. So this is really where the call for IPD meta-analysis comes from. So IPD is individual participant data. We used to say individual patient data, but the word participant is much more inclusive, so we like that. So this is the original raw individual level data that is behind the results in a study. So it's the, if you like, it's the original source material from which the aggregate data were derived. So in an IPD meta-analysis, this is the synthesis of the IPD, not the aggregate data, but the IPD from those multiple studies, again, for the same purpose of summarizing the evidence to come up with overall conclusions to inform clinical practice and decision making. Now, this is increasingly relevant in the advent of stratified medicine. We have different names for this. I'm talking about personalized medicine, precision medicine, whatever funders are using at that particular moment in time, this is what we call it. But basically, it's the tailoring of decisions and understanding about treatment effects and risks for the individual patient, conditional on their characteristics. So not just thinking about overall average population effects. Apologies, I will mention our new textbook. Well, I say new, it's 4 years old now, but we worked very hard on that textbook, and many of the examples are going to be based on the chapters of that textbook. But just before we published it, we looked at how many IPD meta-analyses have been published over time. And, back in the early 90s, there were a few, but then in recent years, there's been quite a dramatic growth up to, we think, well, based on a simple crude search, over 300 articles a year talking about IPD meta-analyses, which was quite exciting. But you could probably see this graph for anything you type into to PubMed. But ignoring that, it's an area of growth. So just for clarity, what do I mean by IPD? So say it's the original source material. So if you got IPD from, say, those 10 hypertensive trials, what would it look like? This is what you would see. So if I merge my data together, I would have a data set that had the trial ID, I would have participant ID, I would know for each participant in each trial what their treatment group was, I'd know their age, I'd know their baseline blood pressure, I'd know their blood pressure over time, maybe 1 year, etc. So I have detailed individual information. I'd have maybe thousands of rows. So obviously this is truncated, but you would have thousands and thousands of rows in hypertensive trials. Whereas in a standard meta-analysis, if you had 10 trials, you probably have 10 rows of data because you just have one result for each study. But now I've got individual level information, so a row for each individual. Moving away from hypertensive trials to cancer trials, here you've got more time to event information. So again, I'd have a study ID, I'd have patient ID, then I'd maybe have some cancer biomarker values. I would have standard prognostic factors in that field, like age and stage of disease, and then time to event information like time of recurrence, final follow-up time, whether individuals were alive or dead at the end of the follow-up. So detailed individual level information, because you'd never have this in a published study. This is obviously what's being provided to you by the original study authors who are collaborating with you on the IPD project. Okay, so why are we doing this? So this was just from the last week. Stephen Sen, eminent statistician in the UK, this was his comment, and it got me annoyed. So he says, I am always puzzled as to why there is such a fuss about IPD. If you have the sufficient statistics, you can produce the same result from the summaries. Now, if that's a view of somebody as eminent as Stephen, that, why do we need IPD? Because we can just get the results from the studies. Clearly, we need to get across the messages about why IPD meta-analysis is important. So hopefully by the end of this lecture, you all have a passion for doing IPD meta-analysis when it's needed. So I'm going to push back against Stephen's quote there. First of all, it's much broader than the actual result itself because, first of all, you can modify the inclusion and exclusion criteria across studies. So it may be appropriate to reinstate individuals into the analysis for a study. For example, if some studies had taken individuals out that were over 70, you could put them back in if that was in your inclusion criteria. We can observe and account for missing data. Okay, so if you've got missing values of prognostic factors, missing outcome values at some time points, we can potentially account for that using some proper statistical methods rather than just throwing those patients away, which is often what happens in practice. We can be gatekeepers to quality, so we can check the results in the original study publications. You'd be amazed how many times you do that and you don't find that the results match. We can inform risk of bias assessments. So, for example, we can use the IPD to just help decide whether a study is of good quality or not. And we may get different results to when if we just use the published information to make that classification. So here's the example from our book. One of these IPD meta-analysis projects led by Leslie Stewart, who's a co-editor of the book, from one of the trials in her IPD meta-analysis, this is the randomization information that she got. So you can see the randomization date for participants in this trial, and I've coded it by group. So clearly, in the first year and a half of the study, Most people are being randomized to the blue group, and then the next part of the study, they're being randomized to the red group. You would not know that from the published information. So it's only with the IPD you can plot that and go, what's happened here? This is not at random, is it? Clearly something has happened. So you can expose problems like this. When we get IPD, we can potentially get more up-to-date information. So if you think a study has followed up people for 6 months when it's published the results, maybe they've carried on and you can get the updated follow-up over the next year. Sometimes there are studies with overlapping participants, and you can identify that with the IPD. If some outcomes are missing in the publication or some summary statistics are not provided, then because we've got the data, we can work out those outcomes of interest. We can work out those summary statistics. So we can reduce the problem of selective outcome reporting. We may get IPD from unpublished studies. So sometimes when you start a collaboration and you identify people you want to get IPD from, they might say to you, oh, by the way, we did this other trial. We haven't published it, but do you want the IPD from that? So again, we may be able to reduce the issue of publication bias. We can standardize the strategy of our analysis. So remember I said to you at the start, I like to be in control. Well, actually with the IPD, I can be in control. So if I wanted to analyze and things with a Cox regression model in every single study, I could now do that. I could check my modeling assumptions. So for example, proportional hazards. I may be wanting to adjust for prognostic factors. So that would increase power, reduce heterogeneity, allow me to produce conditional treatment effects, which I like to think are more appropriate than sort of unconditional treatment effects. We can obtain results for specific subgroups of participants. Like I said, this facilitates individualized medicine. Going beyond trials, and I'll come back on to some examples later, we can look at the accuracy of diagnostic tests better, for example, at multiple thresholds. We can maybe generate and validate prediction models. We can allow for more complicated relationships in our data. So, for example, if we have individual participant data and it's got results for 3 months and 6 months, I can analyze that with maybe a multi-level model and account for the correlation between those time points. Again, because I've got the IPD, I can do that. Without the IPD, I wouldn't know what the correlations were, so it would be very tricky. This is a paper published about 10 years ago in the BMJ, but basically showcasing the fact that data sharing is now the norm. It should be expected, and most journals you submit to require you to have a data sharing statement, and funders, at least in the UK, would expect me to share my data for IPD meta-analyses. So institutions such as the Bill and Melinda Gates Foundation make clear that study reporting and data sharing in medical research are imperative, and the questions there are how, not whether. So this is where we're all moving to and have been moving to for a while. Sharing of data, sharing of information at the patient level, which, and this is anonymized data, of course, which would allow us to do IPD meta-analyses. But the questions we need to ask is, okay, well, do we actually always need to do this? So this is going back to Stephen Sen's quote that, maybe we don't always need to do this. So I've come up with some points which may be helpful to you. But first of all, what I say is, what is the research question? You shouldn't just jump into doing an IPD meta-analysis. It's a big undertaking. Ask yourself, what's the actual research question? And has a previous review been done before to answer this question? So in most areas, people have already done reviews, and they would usually not have done an IPD review. They would look to see a traditional meta-analysis and see what the findings were. Now, what did they find? Maybe they've already answered the question. Maybe there's no need for an IPD meta-analysis. If that review hasn't been done, then ask yourself what aggregate data would be needed to answer that question. So if you're looking at trials, you'd be looking at extracting treatment effects. Are those treatment effects available? Are they for the outcomes that you wanted? Are they for the time points that you wanted? Would they be available in the majority of the studies? Another question is, okay, if aggregate data that you would like is not available as some other issues, then actually, if you got the IPD, would that resolve the problem? So often if you had IPD for a rubbish study, it doesn't really make that study good anymore. It just, got the IPD for a rubbish study. So actually think about getting the IPD, would that resolve the problems that the aggregate data meta-analysis faced? This is important. How much IPD do you think you can actually obtain? is it of sufficient power? I haven't got time to talk about this, but we've done a lot of work on power calculations for IPD meta-analysis. So based on, projected IPD that you think you can get, what would be the anticipated power of the IPD meta-analysis? And you can work that out because you know some characteristics of the trials, for example, how many patients and events are in them, the average age, and things like that, which you can use in the power calculation. How long will it take, do you think, to do the IPD meta-analysis? This is not going to take a few months. This could take 2 years. It may take 2.5, 3 years, depending on how many IPD studies you are actually trying to get. So you need to be very serious about doing this because it's not a quick thing. If you're going to do it, then do you have the resources for obtaining, collecting, checking, and managing the IPD? Do you have statistical expertise and software to analyze the IPD? Clearly, where this is heading is that this is very different to a standard meta-analysis, which is sometimes done by one or two people. Here, you're talking about a big collaboration. So a collaboration involving the original study authors who are providing the IPD, and then lots of people who are doing the IPD meta-analysis project. So clinical teams, statistical teams, people with expertise in data management and harmonization, patient groups, and so forth. This is a big collaborative team effort, which is always necessarily a good thing in medical research. I put in there as well, of course, funding. It's very hard to do these sort of things without funding. So, the time it takes and the length of time, and the number of people involved is usually bigger than like a PhD student would do. PhD students would often do a review in their first chapter or something. That's not really the case. An IPD meta-analysis is more like doing a big cohort study or a big trial or something. It takes a lot of time and resources. I would also ask the question about, are you looking at individualized factors or are you focused on the overall averages? And the more you go down to individualized things, the more you need IPD for. So if you're just interested in overall average treatment effects, then you could well resolve that through standard meta-analysis of aggregate data, assuming that information is expected to be reported. But if you want to come down to maybe conditional treatment effects, looking at subgroup effects, interactions, nonlinear relationships, developing risk prediction models, all these things are more individualized and more complex, and you'll need the individual participant data. IPD might also improve quality. So like I showed you before, it may improve risk of bias assessments. You may be able to improve the inclusion criteria, modeling assumptions, and so forth. And like I said, improving the current analysis methods within the primary studies. So hopefully I've given you an overview of sort of the why we're doing this and when you might start to thinking about doing it. So let's assume that you are going to now do an IPD meta-analysis project. Broadly speaking, what are some of the tasks? Well, if we think about setup tasks, this involves developing a project scope. So what's the question? Who's the target population? Is that the P-codes system, population intervention, etc.? You need to establish the central research team and advisory groups, all those people I talked about in the collaboration. You need to seek in principle agreement from study investigators. This is a really key bit. So this actually means you're going to have to be polite to people and woo them and explain to them why sharing their data is important. Give them some timescales for doing things. You need to think about the sources of IPD. So it could be that we just go to existing trials, but sometimes there may be reasons to get existing databases that would allow us to estimate something that's similar to a trial. Or if you were looking at cohort studies, then we can get IPD from published cohort studies or IPD from e-health records, or so there may be different sources of IPD. We then need to develop data sharing agreements. That's tricky. People actually have to sign contracts and say what they're going to use the data for, and when they will get rid of the data and rights to publications, all these things. Sadly, I think what's happened over time is that as IPD meta-analysis has got more popular, the actual practicalities of doing it have become harder because whereas back in the day, people would just email you the Excel spreadsheet. now it would have to go through a formal data transfer process between organizations. Like I said, we'd normally then have to apply for research funding. We maybe have to get ethics approval. Usually you don't. Usually ethics would say, no, the data is being used in accordance with what it was originally set up for, but you may need to get that exemption from an ethics board. The research team should include diverse groups of people, like I said, but also making sure that it's got people expertise in meta-analysis and doing IPD meta-analyses, and good communication skills. I've mentioned the PICOs. One step that's I've been mentioned before, but is important to do, and a lot of people don't do this, and it's very weird, is a risk of bias assessment. It's strange that in many IPD management projects, people forget to do a risk of bias assessment. There's almost like it just goes out of their head. You know, in a standard systematic review and meta-analysis, we'd always do a quality assessment. But in an IPD meta-analysis, it seems to be that everyone's busy just trying to get the IPD, and then there's almost an assumption that that's resolves anything, but it really doesn't. The question would be, though, when do we do the risk of bias assessment? What I would suggest is that you do the risk of bias assessment firstly based on the published information. So like you would do in a standard systematic review, you extract information from publications, you do the risk of bias assessment. You may be in contact with study investigators at that point. They may be able to help you update information a little bit. At that point, you may even decide to not get IPD from the high risk of bias studies. I think that's important to note. I don't think personally you have to get IPD from every study. There's a sort of built-in belief in standard meta-analysis where you should get all the data from every single study. I don't think that is the case with an IPD meta-analysis, simply because it's a huge amount of effort. I would quite happily focus in on the studies that I felt based on a quality investigation with a low risk of bias studies. If you do then get the IPD, like I've said, you can update your risk of bias checks, because some risk of bias concerns can be alleviated by having the IPD. And like I said, some may only become apparent from checking the IPD. After you've done the risk of bias assessment, there's a big process of checking the data, going back and forth with the original study investigators to resolve any queries, harmonizing the data, and then putting it in a format that's ready for meta-analysis. I've whizzed over that. That could take 18 months to do. It should never be underestimated. The amount of people who end up with doing an IPD meta-analysis, and after 2 years, they've only just got the final data sets, and you know it can be a real burden to them. So just remember that. We then do the meta-analysis, which I'll come on to in a minute, but there's a couple of approaches that we can take for that. We then might do sensitivity analyses. For example, excluding trials that we thought were high risk of bias, or maybe including aggregate data from trials that wouldn't provide their IPD. We then report and disseminate our results. There's a reporting checklist called Prisma IPD, which is for the Prisma extension to IPD meta-analysis projects. Okay, so that's a big, broad overview from aggregate data to what IPD is, sort of the overview of the whole project approach. I'm going to narrow down now on some specifics. So first of all, it's the statistical approaches. So when we do an IPD meta-analysis, there are two options. The first one is a two-stage IPD meta-analysis. This is where in the first stage, we derive aggregate data for each study ourselves. For example, we might do a regression analysis and obtain a treatment effect estimate. And then the second stage, we pool those aggregate data that we've got in a standard meta-analysis model. So this is very similar to a traditional meta-analysis, except for in the first stage, rather than going to study publications and extracting results, I'm actually deriving them myself. So the two-stage approach, we reduce the IPD to aggregate data in each study separately, so a separate analysis in each study, and then we pool those together. Okay, excuse me. So there's a package called IPD Meta, and that's in Stata, and that does all that for you. And so we'll take your IPD, analyze each study separately, pull the results in a few seconds. Brilliant package. And so let's look at this in a bit more detail. So in step one, let's say we're looking at trials and you've got a continuous outcome. You might fit a linear regression model. In a with a binary outcome, we might fit logistic regression. Time to event outcome, we might do a Cox regression. We then estimate our treatment effect, here denoted by theta, and its variance denoted by V. And then the second step, we apply a standard meta-analysis model. So it could be a fixed effect, or what I call a common effect meta-analysis, where we assume the underlying true treatment effect is the same for every trial. And we estimate this theta here. Or we do a random effects meta-analysis, which allows each trial to have their own true treatment effect, and then we assume they're from some distribution, some random effects distribution. So we'd estimate the average across trials and this between study heterogeneity measure. So this is just standard meta-analysis, but we're applying it to the IPD setting in the second stage of a two-stage approach. Right, so now I'm going to come on to more and more examples in the latter half of this talk. So going back to that hypertension trial, the hypertensive meta-analysis was actually an IPD meta-analysis. So I've got 10 trials. Actually, they included about 30,000 participants. So what did we specifically do in the I'll skip that. In the first stage, we're taking the IPD and we're harmonizing it from each study, and then we're going to analyze the data from each study separately in the first stage. So I'm going to use an analysis of covariance. That's just a linear regression model where I'm modeling the final value adjusted for the baseline value. And I'm going to obtain an estimate, therefore, of the mean difference in blood pressure between the treatment and the placebo groups after adjusting for baseline. So I've applied that to each of my 10 trials. And so this is some of the results that I've produced myself because I've got the IPD. So I know how many people are in each group. I know the average age in each group, the mean blood pressure before treatment and at 1 year. And then I've got the treatment effect that I've worked out myself. This is from the linear regression model. And I've got -6 for trial 1, -13 for trial 2, etc. And the bracket there tells us the variance of those estimates. So I've got those 10 trials. I've worked out those summary results myself. So then the second stage, I'm going to do a random effects meta-analysis because I expect there to be heterogeneity. So I'm going to pull results across trials using the disseminating-led approach for random effects meta-analysis. And this is what I find. So this is exactly as we had it before, that the pool result is about -10. Confidence interval is all below 0. So on average across trials, very strong evidence that antihypertensive treatment is beneficial. So that's a standard two-stage IPD meta-analysis, giving us forest plots and results that we all know and love. But just take a step back a little bit. Did we actually need to do that? Is Stevenson right then in this situation? Because what if every single trial had actually done a linear regression analysis and adjusted the baseline? So they would have given me the treatment effect estimate in the publication and its confidence interval. I could have just extracted those results and done the meta-analysis. So I wouldn't have gained anything. And all those 2 years to get that data were a waste of time. Okay, so really important to think about that. So in that situation, the IPD would be giving us nothing new, assuming things like we would include the same patients, that they give us the time points of interest and so forth. But if you wanted to move away from that to look at individualized results, for example, different outcomes, different subgroups of interest, if the original publications, for example, hadn't adjusted for baseline, because a lot of them would look at the final score just on its own, or a change score, which is suboptimal. With the IPD, I can standardize my results. You very quickly get to a position where you're thinking, well, actually, they're unlikely to produce the information I want. And actually, if I had the IPD, I would be able to do a heck of a lot more. The alternative to a two-stage approach is something called a one-stage approach. So in a one-stage approach, this is where we analyze the IPD from all the studies all together in one go. So this approach would be like a multi-level model or a mixed effects model. And clearly, we must account for the clustering of participants within studies. So we can put a random effect on the intercept or a separate intercept in some sense. to allow for that clustering. Otherwise, you're compromising randomization, breaking randomization of those original trials. This is one of the most common mistakes people make, is not accounting for clustering. If you do a one-stage analysis properly and account for the clustering, then usually one-stage and two-stage approaches will give very similar results, especially if you're using the same estimation methods. I haven't got time to go into that, but for example, using restricted maximum likelihood in both or something. But the key exception is when events are rare. So when events are rare, what I mean by that is when the number of participants is small in each trial, or you've only got sparse events in some of the trials, then actually a one-stage analysis is preferred. Because in a one-stage analysis, you analyze the data directly and model the distributions of the data directly. In a two-stage, the first stage analyzes each study separately, and then the second stage, you assume that those study estimates of treatment effects are approximately normally distributed with known variances. That's okay if the study sizes are reasonable, but it's not okay if the studies are small or have sparse events. So if you want to read more about this, then we published a paper last year, I think, in Research Synthesis Methods, two-stage or not two-stage, that is the question, where we go into all of these intricate issues. Let's have a look at some examples. Let's go back to the hypertensive trials. So in these trials, we've got a two-stage result. Now I'm going to use REML estimation, not disseminating lead as I did before. I get results of minus 10.17. If I did a one-stage analysis and probably account for clustering, and again use the same estimation method, I get basically the same result. Okay, and this is because most of these trials are not small, got thousands of individuals. As Stevenson pointed out, we don't need the IPD in that situation. Differences might arise if we use different estimation methods. So in the two-stage, if we use the maximum likelihood estimation rather than restricted maximum likelihood estimation, we might get a lower tau squared, for example. There's some nuances as well in the one-stage approach, which I talk about in the book, where sometimes we end up having to use maximum likelihood estimation. And if we center covariates or don't center, then this can have an influence on our findings. There's some weird things that go on behind the scenes with the one-stage models, which is why generally, as long as data are not small, I prefer a two-stage approach. This second example does have sparse events. This is IPD from 7 trials. So in these 7 studies, I've got these numbers of participants in each of the control and treatment groups. But look at the number of events. Some of these studies have 0 events or just 1 event. If I was to do a one-stage analysis, which is modeling the binomial nature of this data directly and properly, I get an odds ratio from the meta-analysis of 1.91. If I do a two-stage approach, and I have to use continuity corrections to deal with the 0 events, and I have to use approximations of normality and things, then I get a very different odds ratio of 1.31. So that's just one example there of where you do get a difference. And actually modeling the raw data and the IPD is important. Okay, skip that. Right, let's move on to some more examples. So let's showcase some of the reasons why we want to do IPD meta-analysis. And this really looks at individualized predictions. So Paul Gascoigne, he was an England footballer, and after one match, they asked him about whether he thought they would win the tournament, and he said, "I never make predictions, and I never will." And obviously thereby making a prediction. But in healthcare, this is where we're heading. We're heading towards personalized and individualized predictions of treatment and risk. And clearly, if we're thinking about that, then we need IPD to model the individual level relationships in our data. So essentially, we're asking what factors cause some people to have higher risks or higher benefit of treatment compared to others. So commissioners of healthcare want to maximize their treatment benefit and reduce harm for individuals. Pharmaceutical companies may not identify that the treatment works on average, but they may want to identify that it works in some people, but not others. So there's a lot of interest in this. Statistically, this means that what we want to look at in our meta-analyses are interactions between the treatment effect and patient-level covariates, called a treatment covariate interaction. How do covariates interact with treatment effect? This is also known as subgroup effects or effect modifiers. Now, the original studies in a meta-analysis, they're not powered to do this. They're powered on the overall treatment effect. So really, an IPD meta-analysis really comes to the forefront if we're thinking about looking at these individual level relationships, because the power will go up dramatically to look at these individual associations and interactions. This is a IPD meta-analysis that found actually that tamoxifen should only be given to patients who are estrogen receptor positive, because the treatment effects for those that were positive is highly significant and important, whereas those for which it was negative, there wasn't strong evidence that it was important. So that was one of the very first IPD meta-analysis by the Breast Cancer Collaboration Group. So if we want to examine interactions at the patient level, how do we go about doing that? In a two-stage approach, we can, rather than estimating treatment effects on average and pooling those, we can actually model interactions. So we can estimate in each study separately the interaction between a patient-level covariate and treatment effects. And then we can pool those interactions to get an average interaction estimate using a fixed or random effects meta-analysis. In a one-stage model, we can include that interaction in a one-stage model, but we need to be really, really careful, because when you just plug in an interaction in a one-stage model, what happens is you're amalgamating information about variability at the patient level with information about variability across studies. So what you actually need to do is separate those two things out, and there are various ways to do that. For example, centering covariates by their mean. If you want to read more about that, I've given you a reference there. But it's very important to separate those out, bits of information out. Otherwise, you amalgamate across study and within study relationships, and that can lead to bias and confounding. Unpacking this a little bit more, the IPD at the within study level is looking at the change in the treatment effect for changes in the individual covariate value. So, for example, we can estimate how the treatment effect for males compares to the treatment effect for females. So this is explaining within study variability at the patient level. However, what traditional meta-analysis does in meta-regression is examine the across-study relationship. So it examines how the average treatment effect varies across trials as the average covariate value changes. So you might be able to say, how does the treatment effect change across trials as the proportion of males in the study changes? So this is a cross-study relationship, but it's not telling you anything about the individual relationship at all. And often that cross-study relationship can be very badly wrong, and this is called ecological bias or confounding. Let me show you an example of that. Let's go back to our hypertensive trials. Remember, I said to you that the average treatment effect was about -10. So this does well on average, but a question could be, does it do equally well for males as for females? So to do that, we need the IPD, and we need to estimate the difference in the treatment effect for males compared to females, or in other words, the sex times treatment interaction. So now I've done a two-stage IPD meta-analysis where I've estimated that interaction in each of the trials separately, and then I've pooled them. So what we see is when we do that, we get a result that's very close to zero. So there's no evidence here that there's a difference in the effect of hypertensive treatment for males compared to females. The pooled result is 0.77. So even if there was, it's a tiny difference in blood pressure there. Okay, so that's good news. But what would have happened if we had just pooled the results at the traditional meta-analysis level? So remember, this is the pooled result, the patient level interaction of 0.77 from the IPD. So for example, that would say if females, the treatment reduces blood pressure by 20, then for males, it reduces it by 20 compared minus 0.77, so 90.23. No difference, no significance. But if you just done a meta-regression, then the across-study relationship is actually estimated to be 15 and highly significant. So that would suggest that if studies only recruited females and their treatment effects were 20, then studies that only recruited males, their expected treatment effect would be 4.98, so 20 minus this, highly significant. So if you didn't have the IPD, You would not know this, and this may lead to people suggesting that antihypertensive treatment should only be given to females, um, which is clearly not true because the IPD shows a different relationship. This is depicted on this graph. So each of these squares is one of those 10 trials, and the meta regression is this solid black line, which is showing a dramatic trend between the average treatment effects on the y-axis and the proportion male in a trial. So as the proportion male increases, the average treatment effect gets closer to zero. But the gradient of the red lines tells us the relationship, the interaction at the patient level. And particularly in the bigger trials, we see these are pretty flat. And the average of the red gradients would be 0.77. So no difference here. So really remember that. That's ecological bias. Okay, so I'm going to talk for about 5 more minutes. And I'm going to talk about examples. So this is Andrea Leadsom. She was an MP who was around when Brexit was on the go. And she said, I have never and will not start predicting the future ever. I don't do predictions ever. That was on TV. A few hours later, she went on the radio and she said, I'm a very strong arch Brexiteer. I genuinely believe that we have a bright future ahead of us when we leave the EU. There's somebody who doesn't make predictions, but does make predictions. And that's exactly what we're doing all the time in healthcare. Let's quickly go through some examples of where IPD can benefit this area. So nonlinear relationships. This is going back to the hypersensitive trials again and looking for a nonlinear relationship between whether age has an impact on the effect of antihypertensive treatment. And we see this nonlinear relationship here. So the reference group is somebody aged 55, but in those that are younger than 55, we see that there's a significant difference in the treatment effect. But after 55, it plateaus and there's no real evidence. So a nonlinear relationship. Because we've got the data, we can model things on a continuous scale, look at nonlinear relationships and interactions. A related field, risk prediction models, is a paper in the BMJ, which we showed some benefits of IPD for that setting. So in prediction models, we're estimating individual risk. One of the major issues we have is miscalibration. So when we apply those models across countries, they don't calibrate well. So this is an IPD meta-analysis looking at the performance of a particular model in 8 countries, and the calibration slope, which you'd like to be 1. So estimated risks should agree with observed risks. In that situation, it would be 1. The average meta-analysis result is 0.99. So on average, it's fine, but clearly in this study country over here, the calibration is way off, and over here it's way off. So there's huge heterogeneity. But with an IPD meta-analysis, not only can we validate the existing model, we can actually update it and recalibrate it. And maybe that's just a simple recalibration of the intercept of those models. So that's what we were able to do. If you just recalibrate the intercept to each of those countries, then you see that, again, the average meta-analysis result is 1, but now the heterogeneity is gone. And basically, you're very confident that in any one of these countries, the model is going to work well, simply because you've recalibrated the intercept. Again, through an IPD meta-analysis, you'd never be able to do that without the IPD. Doug Altman was one of the first people to promote IPD meta-analysis in the prognosis setting. And he did an IPD meta-analysis looking at whether microvessel density is a prognostic factor in lung cancer. And they got the IPD. They were able to then standardize the results by measurement method, and they were able to adjust for the prognostic values of age and stage of disease and analyze MVD on its continuous scale. And they found that there wasn't any prognostic association with it of MVD. This completely contradicted an earlier aggregate database meta-analysis, which hadn't been able to do any of those things. So this was their meta-analysis result, but other previous meta-analyses had used published data, which is full of publication bias, full of things like dichotomized continuous variables, different methods of measurement, and so forth. And then lastly, test accuracy at multiple thresholds. If you're putting together the results of tests in a meta-analysis, then different studies would use different thresholds to define positive and negative. And if you did a ROC curve, then you would end up with some improper function like this. So an ROC curve should always go up but this comes down. This is because you've got different numbers of studies at each point contributing. Whereas in IPD meta-analysis, we can use the thresholds that we want in every single trial and standardize that. And you end up with this proper ROC curve telling you the relationship between sensitivity and specificity across threshold. I've got two slides I want to show you at the end. First of all, I'm a big fan of IPD meta-analysis, but don't go away thinking that they are always perfect because there can be biases that act in the identification of relevant studies, the decisions about which studies you get IPD from. You're not going to get IPD from all the studies necessarily. It's not foolproof. So just like when Steve McLaren was manager of England and he said we had to reduce the expectations of the England football team, and he certainly did that because he got sacked very soon after. We have to reduce our expectations of IPD meta-analysis. It's not perfect, but if you contrast it to what you could do with a standard meta-analysis, it's way better. So think about the cost, think about the time, think about how you're going to handle things like different methods of measurement and coding across studies, and think about what advanced meta-analysis methods are going to be required. Here's a paper in the BMJ arguing why did it take 90 months to get IPD from one study? And they said the emails we received during the prolonged exchange were all friendly and helpful, but we were hampered by inflexible, formalistic, and slow bureaucratic procedures. Since our first inquiry, we sent 25 emails, filled in 4 data use agreements, and waited 1 year, 7 months. That's just for one trial. And this video is, well, basically what happens when you're trying to sort out a data sharing agreement. If you look at these guys trying to put this ball in the net, this is basically what happens when you try and get your university to speak with another university to get the data, and it goes back and forth like that. Right, so in summary, IPD meta-analysis is synthesizing the raw patient-level data from each study. It could be costly and time-consuming and painful to get IPD, but if you get to that point where you've got it and you've harmonized it, the advantages are huge. In this era of data sharing and individualized medicine and looking at subgroups and interactions, nonlinear relationships, all these things, it's going to be hugely beneficial. And like I said, 2-stage or 1-stage, often 2-stage approach is the most easiest. But many issues still might exist. Here's a website that I've generated to try and disseminate good practice, ipdma.co.uk. I do have a look on there. All the references for this talk are on there. So sorry I've gone a little bit over time, but it was a big topic and I hope that's been helpful, at least giving you a starting point if you're thinking about this area and where to go. Thank you.
Great. Thank you so much, Richard. People in the comments are chiming in. That was amazingly informative. Thank you very much.
Thank you.
If you have a couple of minutes there, we've got a number of questions in the chat.
Yeah, great. I'll
Jingru,
stop sharing.
Jingru, could we kick off with you?
Yeah, sounds good. Hi, Dr. Raleigh.
Hi.
I have a question regarding the easiness of obtaining IPD across different study types, because we have in a traditional AD, like aggregated data meta-analysis, we will want to include as thorough as possible the types of literature, such as published literature and also grid literature. So is there a differences between the easiness of obtaining IPD across this different literature?
Yeah, that's a good question. I don't know whether we know that exactly. Um, I think I mentioned examples where we've got IPD from grey literature that we didn't know about because basically the studies that that provided their IPD also gave us the IPD from those other studies that we didn't know about. Um, I don't know the answer to that. I don't. I think the availability of IPD can vary across different disease fields as well. I think it will depend on who you have on your team. So if there are some big clinical people in your team, they are more likely to be able to persuade people. They are more likely to be able to know where that grey literature is and what those unpublished trials are. So it's very important about getting the right people on board. And if people see that there are big players on board, they will want to join. So there is some, yeah, you have to be quite tactical about these things sometimes. That's the main thing that I can say. Yeah.
Man, you had a related question.
Yeah, I'm just wondering, actually, I think Dr. Riley touched on this thing about like the type of studies might bias the results from the IPD meta-analysis. So I'm wondering if there are some methods or like how to IPD meta-analysis handle this kind of like potential bias of like selective inclusion of the
Yeah.
studies.
Yeah, so we call this availability bias. So is there a systematic difference between trials that would give you their IPD than that wouldn't? Um, I mean, one way of examining this is to think about the published aggregate data results from those trials that do give you IPD and those that don't, and see how similar they are. So on average, are they very similar? And then you may not be so worried about having a subset. But I like to think of it in a different way that actually, if people are not going to share their IPD with you, why is that? Are they trying to hide something? So actually, maybe you're going to get the better quality studies anyway for your IPD. Also, a lot of the time in our IPD meta-analysis, we want to go well beyond what was originally published. So there shouldn't really be a selectivity issue because it's not like you're getting trials based on results you already know about because you haven't analyzed things yet. So it's a bit different than publication bias in a traditional sense, if that makes sense. But definitely comparing the IPD studies and the non-IPD studies for their characteristics, um, average ages, average baseline characteristics, see if there's any systematic differences, countries, regions, time, I think is important. I would always try and do some sort of sensitivity analysis with and without including aggregate data from non-IPD studies. But the issue is the studies that don't give you the IPD, their aggregate data is probably not going to be in the format you want it to be anyway. So that's going to lead to heterogeneity and differences. So it's a bit of a circular argument.
Related question to that. In the educational applications of IPD synthesis that I've seen, there's almost always scores of further studies within the scope of the review where the IPD is not available. Do you see, I guess, what do you see as the value add of trying to loop in findings from the aggregate data? Uh,
I The only place where I've ever really seen it valuable is in when you're looking at average treatment effects. Um, and actually, sometimes what you can find is that the aggregate data from the full set of trials actually has more of an asymmetric funnel plot, whereas the IPD that you get, because you've standardized findings, you've
mhm.
standardized the adjustment factors, you standardized the time points, you standardized the outcome, you may end up with a much more symmetric funnel plot. And so what it shows you actually is that those trials that you didn't get IPD from, they actually cause some asymmetry or small study effects or some differences, which you think are probably down to the fact that either they're lower quality or that you haven't been able to get their data to standardize their analysis. So it can be quite interesting. There's some examples in the book about
Oh,
that.
that's interesting.
Yeah.
Yeah. Yeah. Betsy, do you have a question?
Sure, I'll go for it. Hi, Richard. So
Hi.
good to see you. The thing that I think you didn't talk too much about is missing data, which of course can be a problem within any single study. And I'm wondering how much of a problem it is in your experience working with the IPD data sets that you've worked with. I mean, I can imagine two different scenarios. One where sort of random and just a within study phenomenon that happens in every study. But yeah, I mean, people do structurally choose not to measure things, and that leads to missing data. And then you wonder why is it missing? Because you collect a lot of variables.
Yeah, and this is still a problem, right? In the original study in the first place, you possibly just wouldn't have known about it. So you end up with lots of different weird sorts of missing data problems. So you would have missing data across some patients within the study, but then you'd have some studies that have some variables and don't, some other studies that don't give you those variables. So you have
Right.
some systematically missing variables as well as partially missing data at the patient level. Um, and then you're in a situation of, right, okay, which variables do I include? And so there are huge problems with this. And there are missing data methods coming out to deal with this, which would allow you to use multi-level missing data imputation type methods.
Yeah.
The basic one is to do the imputations separately in each study and then pull the results. But that doesn't necessarily deal with the issue of whole variables being missing in one study compared to another.
Right.
You
That's
have to
been
borrow
my
across.
experience.
Yeah. So you'd have to borrow information across studies. So there are some definite challenges with that, shall we say, because the issue is that these weren't set up as a prospective data collaboration.
Right, exactly. But lots of possibilities maybe for potential future research projects for those
Yeah,
PhD candidates listening,
definitely.
or for you.
Yeah.
Yeah, I
Um,
don't think I'd go down that road. That's too hard for me. But definitely, if people would want to tackle that online, that'd be fantastic. Thank you.
Yeah, and thanks so much for this presentation. It was really nice.
Great to see you, Betsy.
Yeah, likewise.
Yeah.
Noah, are you on? I saw you had a question,
Yeah,
a
I'm here.
cognitive question. Yeah.
I have kind of a low level question, but it's a practical question. So you mentioned that this can take like 2 years from start to finish. And I'm wondering how you deal with reviewers when your literature search was 2 years ago. Because in my field, review cycles take like 3 to 6 months on average. And like over the last year, I've probably had three different reviewers say, oh, Cochrane says that your search needs to be within the last 3 months. And when I reply, that's literally impossible because as you can see, this was submitted 4 months ago and you're just now reading it for the first time. And like long story short, I cannot get an accept on these papers until reviewer two is happy with the search date that is completely inconsequential to the results. So I'm wondering how you deal with this with IPD, given that the time, like it's hard enough with me with 6 months. I'm wondering how you deal with it with 2 years.
It is such a big issue. And it's such a naivety of those reviewers when they come back and say to you, can you just update this? And you go, really? They really just do not understand what you've done and how long it's taken. Because your funding's run out as well. So you can't suddenly start getting IPD from. So I would then have to be really strong and push back and say, look, and I hope things like this textbook would help and say, look, in this guidance it says these specific things about how long it takes. It's unfair of you to ask us to update this because we will still be in a position where we're 2 years behind by the time you get this back. So I think you have to be strong and push back in those situations. It's unfair on researchers to constantly demand those things. It's not comparable to a standard meta-analysis
Yeah,
situation.
and mine is a standard meta-analysis, but it's still one of those things where it's time consuming. And if a review cycle takes 3 months, you are never going to have
No,
the search data within 3 months. And so I mean I don't perhaps it's just an issue of reviewers and editors and things like that because in my similar one that's recent, we've tried to push back and essentially the editor's comments have been the person is right. That's what the Cochrane guidelines say. And I'm like, there's a big difference between medicine, where you might have a 2 week review cycle, and education, where you have a 6 month review cycle. But
absolutely.
yeah, it's just very frustrating. So I'm on one hand, I'm glad to hear I'm not the only one dealing with it. On the other hand, I'm sorry because I can't imagine putting 2 years worth of stuff in, like work into this, just to deal with the same issue that I'm dealing with right now. Because it's frustrating enough with a 6 month delay. I can't imagine it if I was doing it for 2 years.
Yeah.
Okay.
Yeah, I feel your pain. But I do think we have to push back with reviewers, particularly reviewer
Yeah.
two.
Yeah.
Yeah. So I'm cognizant of time here, and this is like the one time in the seminar series where I really wish we were in person so that we could just all go around the corner to the pub and keep up the
Oh, that'd be lovely.
conversation
Yeah.
about IPD. But so
Let's do
I
that.
guess
Let's do that in the future.
yeah, let's. And in the meantime, I guess we can all raise a virtual toast to Richard. Thank you so much for joining us and sharing this wealth of knowledge about IPD. We really appreciate it. And this is the conclusion of the seminar series for spring 2025. It's the end of my tenure as chair of the SIG. I'm leaving it in the capable hands of Carlton and Derek. Who have told me that they're planning to continue the seminar in the fall of next year. So we'll be back. Stay tuned. And thank you all for coming.
Thank you so much, everybody. Cheers.
Cheers. Thanks so much.